Okay, let's get started. So if you haven't picked up your homework 5 or quiz, what is it, 14? And some people haven't picked up their quiz 12 or 13. I'm not sure if there are any left, but if you haven't picked that up. Okay, so are there any questions before we start? So remember, no lab next week at all, and no class Friday. There is class Wednesday, but no class Friday. So, Merry Christmas in March. So, any questions though? And the really cool thing is that we're about a week ahead of where I had us on the schedule. So we can afford to slow down a little bit. I don't want to get too far behind because we may want to get to some interesting things at the end. But yeah.
When we were converting the CFG to PDA,
Mm-hmm.
you had for the 0 to the n, 1 to the n, we had 2 ways of doing it. Do you know what I'm talking about?
Yes.
Like we had a generic way, something that like versus the first one that we did. What's the difference?
There is a difference. So the one way that we can do it, so I'll call it number 1 and number 2. So the first way that we did it directly was we had. So I'm not going to draw the whole thing, but we had something that looks like this, right? So we pushed the $sign on, and then put the zeros on the stack, and then the other state reads 1 and pops a 0, and then finally pops off the $sign. The other way you can go is to make a grammar for 0 to the n, 1 to the n, and then convert it directly. So that would involve the 4 base states that we know and love, and then we would need a transition for reading and popping off the characters, as well as the multiple transitions that involve like each of the rules. So the first one is obviously smaller because it has fewer states, but we have to think a little bit of how to actually make the machine work. The other one is systematic in that as long as you have a grammar for it, you can make a PDA for it. So we directly made the grammar in the second case and directly made the PDA in the first one. So extending what your question was, what if we wanted to make a grammar for 0 to the n, 1 to the n? Well, clearly, this is one of them. But what's another way we can make a grammar for it?
I mean, there's like an infinite number of ways. We could have like a bunch of unit rules, for example.
Yeah, but like in a reasonable way. I mean, if we had a DFA, we can just add another state that does nothing. But I mean, like actually making the grammar. So we can make it directly like this, but what's another way we can make it? Well, we have 2 PDAs right here. Is there a way that I can convert a PDA to a CFG? Yeah, we actually covered that. We finished it last time. So if we convert these 2 PDAs into a CFG, that gives us another CFG. So what you should note about pretty much everything that we've done is there's usually a direct way that you can go, but the more computationally correct way often is to do a conversion from something else that you know. So which of these PDAs is easier to make? I think the left one, right? Because to make directly, I mean. Which one's easier to make directly? I think the first one, because we didn't need any knowledge about how the conversions actually worked in order to do that. But the thing is, we have to actually think about how it works. Versus if we just had a simple grammar, we can just convert it to a PDA just using the conversion and don't have to think about it. So there's always 2 ways of approaching it. But yeah, just because we have 2 different PDAs for the same language, we can definitely, of course, have that. And in fact, the first transition and the last one are both the same. So it could be that two different PDAs have really similar behavior, but be completely different structurally and still have the same language. And these two are an example of that. Yeah.
Can there be a language that doesn't have grammar?
Yes, and we're going to actually talk about that today. You mean a context-free grammar? Yes. Yeah, that's what we're going to get to today.
And can you have a PDA for something that doesn't have a context?
No. So we showed last time that, or at least we finished it last time, that you can convert a CFG into a PDA and PDA to a CFG, so they're equivalent. So if there's no way to make a grammar for a language, then there's no way to make a PDA for it. Because if they're Word, then I can just convert it. Any other questions? Yeah.
It might be explained later because we're going to be going over it.
Uh-huh.
Is there any type of language that just can't be represented at all? Because we originally thought we couldn't represent 0 to the end, 1 to the end with anything, but then we made a new model. So
right.
Is the next one going to be possible to represent through state machine?
So in terms of the PDA state machine, yes. In terms of of any type of state machine, also yes. But it's not the one that we're going to talk about here. And in fact, the really sad thing is the vast majority of languages, and by that I mean a vanishingly small fraction of languages can be represented. Every single other one, 99.9999 whatever percent, all of them can't be represented by any state machine of any kind. Isn't that sad? And the really interesting thing is we can prove that in 5 minutes. That really very important statement we can prove really quickly. Isn't that amazing? So that's one of the cool things I like about this stuff. But let's talk about the elephant in the room, which is are there any languages that are not context-free? And what did we start to talk about last time? So I'll try to, you can go. Yeah, so we were trying to establish a pumping lemma, but we weren't quite there. So let's go back to where we were. So we tried to establish two facts, or at least establish the facts of, well, if I have a grammar in CNF and look at its parse tree for some string, well, we know then it's a binary tree because every variable is going to make two variables unless you're at the bottom. So everywhere else in the tree is always a binary tree. Then we noticed in this example right here, if we make the tree tall enough, which means make the string it generates long enough, if we make the tree tall enough, then if we look at going from the top to the bottom, then at some point there must be a variable that repeats. Because if I just make it taller and taller and taller, at some point there must be a repetition in variables. So we looked at a repetition, let's just say this one, and we did some basic experiments. Like if we take the bigger parse tree, the one for the first A right here, and I copy and paste it down to where the second occurrence of that variable is, well, I still have a parse tree, and we can show a different string can be generated because we just made another parse tree. So what we talked about before and what we established was that this string, if I have some decomposition of this form, if I repeat some number of occurrences of v and the same number for y, then that will always stay in the language. So there's some decomposition into those 5 parts, such that if you pump the second and the fourth piece, then you will always stay in the language. And then we established another fact last time, that if we look at the worst thing that can possibly happen, which is if the second variable, the second occurrence of A, is right below the first one, then what could happen is, well, one side of the parse tree coincides. So the left side of the A's are coinciding together, but the right side of the first A is not coinciding with the second one. So in other words, so if we look at this half of the tree, well, the first occurrence of A, the second occurrence of A never touches that side. And we know each variable must make something of the string, which tells us that one of the 2 sides must be some character, must generate something. So that tells us that, well, the V part is on the left, the Y part's on the right. One of those 2 is not empty. It can't be the case that both of them are empty. So that tells us that the length of Vy together is at least 1. One of those 2 is not empty. I don't know which one necessarily. Okay, does that make sense? Okay, so what else can we say? Let's go back here. So there's one more fact that I think we can establish about this. So here's our parse tree again. Okay, what's going on? Okay, I'm gonna have to quit, come back in. I don't know what in the world just happened, but okay. So here's our parse tree, and let's see. Let's suppose that we look at the following. So here's our variable s at the very top. And let's look at the following. Suppose that the first occurrence of A is at the very top, or as close to the top as possible of the parse tree. And then we have the path down, and then the other occurrence of A is somewhere else. We don't really care about that one. So what does that tell us here? Well, let's say that to get a variable to repeat the derived string W has length at least P. So some number P, let's just say as long as it's at least that length, then there must be a repetition in the variables no matter what. And we know that that is the case because there are only a certain number of variables. And we could figure out what that number is, but or at least at the lower bound for what it needs to be. But we're not really concerned with that. Okay, so let's see. So as long as it has length at least P, then there's a repetition in the variables. So if the length of W is exactly equal to P, do we still get a repetition in the variables? So I said as long as it has length at least P, then we get a repetition. What if it has length exactly equal to P? I think that's still true. Right, because as long as it's length at least P, so greater than or equal to, we're good. And if it's equal to, therefore it must be good. So let's just say that we have length exactly equal to P. So W1, W2, W3, up to WP, although that doesn't really matter. So let's look at this. So let's look at the parse tree that the first A makes. So the parse tree that the first A makes. Well, since it's right below the start variable, it's got to make all of the left side, and it can't make all of the right side, but it must make something. So let's just say it makes something that looks like this. And of course, the second occurrence of A also makes something. Actually, I'm going to get rid of the W1 part because I'm going to put some letters below it, and I don't want it to interfere. So let's just say that this is the situation that happens. Well, let's start naming the 5 pieces. Well, let's see. Where's the U part? It's smushed all the way to the left side. Technical term, by the way. Smushed over to the left side. So the U part is over here. The V part is the next one. So that's this part. The X part is, of course, the next one. The Y part's here. And the Z part's here. Well, the part that we're mainly concerned about is the part that repeats. So if we look at the parse tree for the first occurrence of A, the big blue parse tree, well, the entire string right here has length exactly equal to P. Well, what is VXY in relation to P? Well, P is the entire string's length. And so what does VXY have to be in relation to that?
It would be P minus the length of VXY.
So let's look at this. So this whole thing is length P. So what is VXY in relation to P? Yeah, it's at most P. That's all I wanted to establish here. So as long as if we have a string of length exactly equal to P, then VXY has length at most P, because it's only some of the part that's generated. Well, what if the string's length is more than P? What can we do? So I'm not going to go through the argument, but the idea is, let's look at the 2 occurrences of a repeated variable as close to the bottom as possible. Then, as long as we look at the ones that are close to the bottom as possible, we get the same result out of this. Because if we put the start variable right above it, well, it makes a string of length. We can show that it generates a string of length exactly equal to P. So I'm not going to go through the entire argument for that. But this tells us that the part that involves the pumping, right here, the V, the X, and the Y part together, because V and the Y part are the ones we are going to repeat together, that part has length at most P. So the third fact that we can establish here is that the VXY part has length at most P. Okay, so we're actually able to state the, how many words is that? The 5 most hated words in this entire class, which are the pumping lemma for context-free languages. Context-free is one word because it's hyphenated. That's what I was thinking. Like, was it 6 or 5? So, yeah. Every time I write the word pumping, I think pumpkin. So, that's something I should do if I'm teaching the class in the fall. I should bring some pumpkins on for this. Okay, so what does this say? So it's actually really similar to the one for regular languages, but there are slight differences, as you might expect. So starting off great, I can't spell let. Let L be a CFL, a context-free language. Then there is a pumpkin constant. I should start calling that from now on. Pumpkin constant P for L. Then what we did was, in what we were doing, we were making a parse tree that was really big. So because it has a parse tree, that means that the grammar or whatever can actually make the string. So it's in the language of it's in L, which is the language we're talking about. And it has to have a length at least a certain number P. So what do you think is going to appear next? Then, for all strings in the language of length, what? At least P, which is exactly the same statement as for the regular language one. So then for all W in L with the length of W at least P, so in the pumping lemma statement before, do we need to look at all decompositions or just one? Not showing that the lemma is false or whatever, or trying to get a contradiction. Just what the lemma says. Do we care about all decompositions or just one? Well, that's when we're trying to get a contradiction. So here, I think we only need one. And the reason for that is, as long as there's some way to break this string up into 5 pieces, I can repeat it as much as I want to. I don't care about any other way to decompose it. So this tells us there is a decomposition of W into U, V, X, Y, Z. So that, and then we got 3 conditions, just like before. So in fact, there are only 2 differences between, I guess 3, at this point from the regular language one. Well, it's called pumping lemma for context-free languages, so I think that's a little different. L has to be a CFL here. Well, every regular language is a CFL anyway. So it has to be a CFL. And we're breaking W into 5 parts instead of 3. But everything else is the same. So what are the 3 conditions? Well, the one we just talked about. Oh, go ahead. Sorry.
Sorry. With the regular language pumping lemma, we're like trying to prove that the language is not regular. What are we trying to use?
So we're going to eventually try to prove some language is not context-free. So it's the same idea, but now for context-free. Other questions? Okay, so the one we just derived was that the length of V, X, Y, the 3 middle pieces, is at most P. Again, this one is not actually truly required, but it's really, 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 really useful. It makes our lives so much easier. Okay, so that part is true. The one we derived last time was the length of Vy, so excluding the middle part X, is at least 1. So one of the 2 pumped pieces is not empty. Well, they both might not be empty, but one of them is for sure. And then the final one, which we also made last time, was u v to the I, x y to the I, z is in L for all I at least 0. So here's something that we should note here. Where are the pumped pieces in this case? So which of the 5 pieces are the ones we're going to put more copies of into the string?
They are the ones sandwiched between the left side and the right side.
No, I'm just talking about right here. The
V and Y.
The V and Y part. So let's see. Well, note the VXY has length at most P, right? Does that involve the prefix U at the front of the string? No. So take note of that, because that tells us that the parts that are involved with pumping are not at the front of the string necessarily. They can be anywhere because we have no stipulation on how small or big the beginning of the string is, U. We have no stipulation on that. So the pumping lemma here is more complicated in the sense that you are not necessarily pumping at the front of the string. You could be pumping anywhere in the string. Okay? And when we're going to do our first example right here, we're going to see that in action. But are there any questions about why that's the case? Okay, so let's actually do our first example. So this one may seem a little familiar, which is instead of 0 to the n, 1 to the n, it's 0 to the n, 1 to the n, 2 to the n. So it's exactly the same language except you put 2's at the end. And notice that it's the same number of 0's, 1's, and 2's in all cases. So what do you think this language is? So is this language regular, first off? No, and what would an example string be to try to prove that?
0 to
Yeah, just put a P where the N is, right? So it's not regular, but that doesn't imply it's not context-free. So suppose we had no idea that whether this guy was regular or not. We don't know if it's regular. If we show it's not context-free, what does that imply about its regularity? It can't be regular because every regular language is context-free. So if it's not context-free, it can't be regular. So that's something that a lot of people do where they just show us not context-free to show that it's not regular. But if you show it's not regular, it may or may not be context-free. Okay, so what do you think this one is? Context-free or not? I wouldn't lead you guys down the garden path, right? Okay, so this one is not context-free. So no grammar, no PDA could ever recognize this language. One thing that, so if you were evil, what I would do, what you could do is to ask your friend, hey, I want a CFG for this language. Can you make one for me? And your friend will spend an eternity trying to make one because there doesn't exist one. So, but in all seriousness, what I would recommend you do, or at least try, is try to make a grammar for this, or try to make a PDA for this. So what would an attempt for making a PDA for this be? Well, let's follow our 0 to the n, 1 to the n example, which is we push the zeros on the stack, and then as we read the ones, we're going to pop the zeros off the stack. But what about the 2's? Well, if we push the zeros on and pop them off when we see the ones, now there's nothing on the stack to check that the numbers is the same. So here's something interesting. What if I have two stacks? Could I recognize this language?
Yeah, couldn't you do the normal thing, but whenever we pop a 1, we push it, or just something so that whenever we're getting rid of the 0, we're also keeping track of the 1, so that for the 2, we just pop the...
Right. So as we read the zeros, put them on the first stack. When I read the 1s, put them on the second stack. When I see the 2s, pop them off both stacks at the same time, because it has to be the same number. So if I can claim that this is not context-free, what does that tell us about two-stack PDAs? Are they more powerful? Yes, because of this language. Isn't that cool? That the fact that PDAs have one stack is actually important. It's not, you can just have any number of stacks. One is actually important. So let's get to the meat of this. So it's not context-free, or I want to show it's not context-free. How would we start in doing this?
We first assume that it is.
Assume that it is. So assume L is context-free. And the great thing about these is that these proofs start almost exactly the same as the other ones, because the structure of the two lemmas is very close. So we assume it's context-free. What do we usually would do after that?
Then there exists.
Yeah, there exists a pumping constant P. So I'm going to shorthand that. There exists a P for L. You should write there exists a pumping constant P for L in English, but it's just I'm shorthanding it. Because this is not the important part. The important part is how do you actually pump out of the language? Because it's going to be more complicated than the regular language case. Okay, so once we have this constant P, what do we do after that?
Choose a word.
Yeah, choose a string. Yep. Choose a string, W equal to, and what would be a example in this case? Actually, we already talked about it.
Replacing the end with these.
Yeah. So the logic in making a string is very often similar for the context-free case. And this string will work. But the key thing to remember here is we're not just pumping the zeros like we did with the regular case. So regular, we pumped at the front of the string within the first P characters. Here, we pump a segment of length at most P anywhere in the string. So that's just something to keep in mind. Okay? Okay. So are we... Do you have a question? Okay. So when we're trying to show that we can pump out of the language, well, which decompositions into 5 pieces are we going to look at? Are we going to look at one of them, or several of them, or all of them? All of them. So we need to look at all decompositions of W into U, V, X, Y, Z. So remember when we were doing regular language proofs, we said like did we do X, Y, Z as the 3 pieces? Yeah. So we said that the X part was 0 to the alpha, Y was 0 to the beta, Nightmares coming back of those? Okay. So great thing here is we're going to be less formal with that. So we're not going to say alpha, beta, whatever. Unless it's absolutely necessary, we're just going to ignore it. Okay? So what could happen here? So remember, the VXY segment that involves the pumped parts, well, that could be anywhere in the string. Well, what if it was only in the zeros? So let's look at this case. So VXY only contains zeros. So is there a way that we can pump to get out of the language if both of the pumped pieces are within only the zeros? So by that I mean, if I insert an additional copy of V and Y into the string, am I going to leave the language? Yeah, what has to happen with this string in this language? Well, we have exactly P zeros at the front, so one of V or Y, I don't know which, is non-empty. So if I put another copy of them in, I'm going to get more zeros out of it. So that means the number of zeros went up. But what happened to the number of ones and twos? They stayed the same. So if we pump up the jam to I equals 2, that was a joke by the way, pump up to I equals 2, then the number of zeros goes up, but number of ones, number of twos, unchanged. Isn't writing proofs like this way easier? Just write it in English. Yeah, because it's just like now you gotta, if you wanted to do this formally, you would have to introduce 5 variables, like alpha, beta, gamma, delta, something else. So it'd just be way too difficult to do. Just write it in English here, unless it's absolutely necessary. Okay, so what if VXY, remember, could be anywhere in the string at all? So what if they were only in the ones? So if the V part was in the ones and the Y part was also in the ones, what could we do then? It's same argument. What if they were in the twos? Same argument, because we require that all 3 segments are the same. So I'm going to squash both of those into one bullet point. So VXY only contains ones or only twos. So then same as before, no difference. Or not same, similar. Because in those cases, either the number of ones went up or the number of twos went up, but the other 2 counts stayed exactly the same. So if the number of ones went up, the number of zeros and twos don't change. And if the number of twos went up, then the number of zeros and ones doesn't change. Okay? Any questions about that? Cool. So we pumped it out in every single possible case, right? No. What are some cases we didn't touch?
V is in 0, X is in 1, Y is in 2.
Could that happen? We'll return to that, but yeah. So let's look at that, a similar case. So what I think you were saying is the VXY middle piece contains a 0 and a 1. So this one really is a technical term. It straddles the boundary between the zeros and the ones. So it's sitting like some of it's in the zeros, some of it's in the ones. It's not uniformly in one of the segments here. So what if the VXY part contains a 0 and a 1? Could it contain 2's? No. Why not?
Is it most length P?
Is at most length P. But then here we have a run of 1's of length P. So it's not possible to go across all the 1's to hit a 2. So it only contains a 0 and a 1. It can't contain 2's. So what can we do to pump out of the language in this case?
Do something similar where we have a different number of 1's than 2's. So just if we choose like I equals 2, we should have a different number of 0's and 1's and 2.
Not necessarily different number of 0's and 1's, but
I'm saying those two together is more than.
right. So if we pump up to I equals 2, then either number of zeros went up or number of 1's went up, or both, because it could be the case, but the number of 2's unchanged. So what's another case that could happen? So we just handled the case of where it straddles the 0-1 boundary. What is another case that could happen? The 1 and 2's, right. So if VXY contains a 1 and a 2, then what can we say here?
Same idea.
Yeah, similar idea.
0 is the one that doesn't change.
So similar idea. And I'm just going to put in here, it's not necessary, but the number of zeros is unchanged here. But wait, it could be the case that the VXY part has a 0, 1, and a 2. Or can it? No, it can't. Why?
Because, as you mentioned before, there's a p number of 1's, and VXY can only be less than or equals p.
Exactly. So since VXY's length is at most p, it's impossible for VXY to contain 0, 1, and 2. And for that reason, we've handled every decomposition. Because it's either going to be uniformly in the zeros, 1's, or the 2's, but it's also the case that it straddles the boundary of one of those two, between two segments, but it can't have all three segments at the same time. So we handled all decompositions, and we pumped out of the language in each one. So what can we conclude? It's not context-free. So L is not context-free. Okay, any questions on how that went? Yeah.
Similar to the question we had before, if there is no word that satisfies being in the language and the length being greater than equal to p, is that the same thing?
Well, so let's see. So where is it? So if there's no string in the language of length at least p, then every string in the language must have length at most p minus 1, which means there's only a finite number of strings in there. And It's regular, and then therefore it's context free. But yeah, so if this were true, then yeah, so if there is a string in here, then you can always pump it. Any other questions? Okay, I think you guys want to do another example to try to solidify it more? Or do you want to move on to something else? Yeah, let's do another example. So this one's actually kind of similar to the one you'll see on your quiz. So let's look at the language, I'm going to call it L2, to be, so it's not going to be 0 to the n, 1 to the n, 2 to the n. It's going to be 0 to the I, 1 to the j, 2 to the k, where I is less than or equal to j, which is less than or equal to k. And since we don't have a lot of time, we're not going to complete this, so we'll get started. One thing that I should mention is, so I'm not going to prove it here, but an interesting result is if a language L is unary, and I'll explain what that means in a second, then L is regular if and only if L is context-free. So this actually has really profound implications, as we'll see in a second. So unary, what that means is there's only one character in the alphabet. So remember like the language of perfect squares where we had 0 to the n squared? So the strings were just all zeros. That's what it means to be a unary language. So that says that L is regular if and only if it's context-free. So if it's regular, it's context-free, which we already know. But also, if it's unary, then if it's context-free, it also is regular, which is pretty amazing. So what did we establish about perfect squares and primes before? Yeah, they're not regular. And if you believe me, I hope you do, if you believe what this says, what do we know about whether they're context-free or not? They're not context-free either. But, so here's the really amazing implication of this. So, context-free grammars are the pinnacle of every single compiler pretty much out there. So that tells us that no CFG can recognize the primes, because if we have the language of primes, which is all zeros, well, that tells us it's not context-free, so there's no grammar for it. But that also tells us that no compiler in existence can verify whether your program that computes primes is correct or not. Because if it could verify your program's correct, then it can recognize the primes language, but it can't. So the compiler can't verify your program of whether, if you are checking whether something's a prime, whether it's correct or not. It's impossible. Isn't that amazing? That simple fact can lead to something profound like that. So I guess we're not going to have a lot of time to talk about this language, but so let's just do the string here. So which string would you pick in this case? So the suggestion was this one. So p plus 2, I think. So this will not work. Yeah, go ahead. Yeah, set them all equal to p. The reason for this is you want, in this case, whenever you're dealing with less than or equal to be right on the borderline of being not in the language. So if I delete 1, 1 or 1, 2, one instance of two, then we're out of the language. Whereas in before, if I delete one of them, then I'm still in the language. So whenever you're dealing with pumping lemma style proofs, always pick a string that is right on the borderline of being not in the language. So that's my $5 million advice to you guys. And with that, I'll see you on Monday.